Physics 2212, Lab 3, brought to you by yours truly, Jake Bernstein. I'm going to go pretty fast through this introductory stuff just because we have a lot to touch on this lab, but a brief overview is first I'll give you an introduction, then experimental results, and finally a discussion and conclusion. So the purpose of this lab is to empirically corroborate key physics principles relating to RC and simple series circuits. And we're going to go through a bunch of different circuits throughout the lab and compare measured values of current and voltage to calculated values. So one of the most important concepts in this lab is Ohm's law, and Ohm's law provides an empirical relationship between voltage and current and resistance, in that V equals IR. Secondly, the loop rule states that the sum of the voltage differences across the components in a closed loop is equal to 0, and the node rule is kind of similar, and it states that the total current entering a component in an electrical circuit that is closed is equal to the total current leaving that circuit. Here are some key formula: Ohm's law, the law of capacitance, and the loop rule, as well as the derivation of the RC time constant, which I won't go through because we're pressed for time, but feel free to pause and check that out. All right, so part one, we have this setup listed right there, and it's a simple series circuit of two 1.5 volt batteries, two resistors, one 47 ohm, one 100 ohm, and then two ammeters implemented in series. The predicted current, we have the relationship V equals IR, so divide by R, you have I equals the voltage divided by resistance, which is predicted to be 0.204 amps, and the measured current in the circuit listed above is 0.0188 amps. If you reverse the ammeter, that'd just be the negative of the value. Part two, now we place a voltmeter in place of an ammeter. And incidentally, our predicted current is 0, and the predicted voltage is 3 volts. This is because the voltmeter has a resistance that is essentially infinite, meaning that no current travels through the circuit. And this is concurrent with the measured value, which was negligible. Part three, examining voltage through these different components. We remove the voltmeter in series, and we calculated the voltage drop as such, given through Ohm's law relationship. Part four, we have an ammeter now connected in parallel, kind of transcending that 100 ohm resistor. And since the current takes the path of least resistance and the ammeter doesn't have resistance, it basically acts as another wire. So the current goes up through the battery, right down through the 47 ohm, and then it takes the ammeter route rather than going through the 100 ohm. So our predicted current is 0.0638 amps, which is pretty much the same as the measured current of 0.064. Next up, we have part five, which is just calculating the resistance given the measured voltage and current. For the 47 ohm, we got 50.96 ohm, which is kind of close. And then for the 100 ohm, we got 106.4 ohm, which is, again, not spot on, but getting there. All right, for part six, instead of a simple series circuit, we now have a circuit composed of a resistor and a capacitor. So we have, again, 3 volt battery. Now we have a 1 farad capacitor, and then 2 light bulbs with resistance as shown in the diagram. So for the 10 ohm resistor, we first charged it by connecting it to a battery. That should read 1 farad capacitor. So for the 1 farad capacitor, we charged it, and it took about 11.2 seconds. And then we disconnected the battery. We had a charged capacitor of 1 farad, and we connected it to the 10 ohm and the 20 ohm light bulbs. So for charging, it took 11.2 seconds for 10 ohm and 23.2 seconds for the 20 ohm. And then for discharging, that's just connecting it to the light bulb. We have 11.4 seconds and 24.3 seconds, respectively. Now the predicted time constant is just RC, 10 seconds and 20 seconds. So the bigger picture of all this is that the overarching physics principles, such as Ohm's law, the node rule, and various others, were verified through our results, and we were able to predict the behavior of these circuit configurations containing resistors and capacitors using these principles. So some possible errors that we might have encountered throughout the lab is that the internal resistance of the wires and the battery are not negligible in a non-ideal circuit. I'll get more into that in the next slide. Another one we have is an inaccurate recording of time constants due to human error on the stopwatch. And then the multimeter measurements, as they're very close, they're not always exactly precise, so that could be a possible error. Now, conclusion, I'll let you read the what if question. And the answer to that is, if we charge the capacitor with no resistor in the circuit, as per the ideal model and the equation for the RC time constant, since there's no resistance in the capacitor, it would take no time for the capacitor to reach full charge. In real life, however, the value would be non-zero, but still quite small, as we record a value of 0.3 seconds when the configuration was attained. This is because there's an internal resistance in the wire in the battery that is not accounted for in an ideal circuit model. This is the leading cause of our disparities between measured and predicted current throughout the lab. Alrighty, that's it. I hope you enjoyed, and have a good rest of your day.